there are three possibilities of solution for system linear equation. The first one, we got inconsistent system or no solution. An inconsistent system occurs when the system has no solution at all. This usually happens when two or more equations contradict to each other. For example, in a matrix form, when you simplify using row equation, you will get a row like the example, which means no matter what values you plug into x, y or z, you're gonna get a false statement like 0 equals 1. This signals that the system is inconsistent. For example, if you try the example below, you're gonna get 0 equals 1. Impossible. So the second one, we got infinitely many solutions. A system has infinitely many solutions when the equations describe the same line or same plane, meaning all points on one equation are also points of others. In a matrix form, after using row reduction, you're gonna get something like 0, 0, 0, 0, which shows that one equation is dependent on another, not independent. This means some variables are free variables. They can take any value. Other variables depend on these variables. For example, if you simplify and you solve the equation, the matrix below, you're gonna get infinitely many solutions where y is free and x equals to 2 minus y. You're gonna get if you answer the question. The third and the last is uniquely solution. A unique solution means that there is exactly one and only one set of value for the variables that satisfy all the equations. After you apply a row reduction, you will get a matrix where each variable has a clear and unique value, no contradiction and no free variables. This happens when all equations are independent, the system is consistent, the number of independent equations equals the number of unknowns. Using a Gaussian elimination, you will get y equals 1 and x equals 1 from the example below.
There are three methods to solve system of linear equations. The first one is row reduction. Row reduction is a method for solving system of linear equations by transforming the augmented matrix using elementary row operations. For Gaussian elimination, the first step is to identify the leftmost column that produces leading one and does not consist entirely of 0. Second, perform elementary row operations to produce 0 at all entries under the leading one. Step 3. Cover the top row with leading one and begin again with step 1 applied to the remaining submatrix. Step 4 is to begin again step 2 to perform elementary row operations to produce 0 at all entries under the leading one, and finally begin again step 3, cover the top row with leading one and identify the leftmost column that does not consist entirely of 0. For Gauss-Jordan elimination, repeat the first until 5th step from Gaussian elimination, and then at the last non-zero row and working upward, identify leading one and perform elementary row operations of each row above to produce 0 above the leading one. And finally, cover the row and repeat step 6 to the remaining submatrix.
Next, we have the inverse method. When can we use the inverse method? Number 1, the system must have same number of equations as variables and the coefficient matrix must be invertible. For step 1, express the system in matrix form AX equals to B. Step 2, find the inverse of matrix A. And for step 3, multiply both sides of the equation with inverse A.
The next method to solve system of linear equations is by using the Cramer's rule. When can we use the Cramer's rule? The system of linear equation must be a square matrix, that is, they have the same number of equations and variables. Other than that, the determinant of the coefficient matrix must not equal to 0. Using the formula where x equals to the determinant of matrix A over the determinant of matrix AI, where AI is the matrix formed by replacing the ith column of the matrix, we can find the answers for the system of linear equations. Here, we have provided an example of using the Cramer's rule to solve for the variable column matrix.
There are many ways to solve the system of linear equations, and one of them is the Gaussian elimination. This method is particularly important if you would like to get the REF form as your final result. Now, let's have a look at this question. Don't panic, we'll guide you step by step. What's important is that we need to remember the elementary row operations. Don't worry, we will show you at each steps which exact EROs that we have applied. Step 1 is for us to rewrite the SLE to its augmented matrix form. Then, step 2, we need to look at the entries. We need to swap rows in such a way that would allow us to have leading ones in each row later on. In this case, that is, row 3 will be swapped with row 1 and row 1 will be swapped with row 3. Step 3. Let's have a look at the first row. Under the leading one, we need to produce zeros. Let's do it one at a time, starting with the circled entry. In order for us to do that, we are going to do an ERO, R2 minus 3R1. Great! We're still not done yet. We still have one more entry that is not a zero, and that is located in row 3. The entry is 2, which I have circled. So, meaning, step 4, continue by doing another ERO, R3 minus 2R1. Yes! We have successfully processed our first column. Under our leading one, we have zeros. So, meaning, step 5, let's cover our pivot row so that we can focus on continuing our second column. We need to produce a leading one, but here we have 10. So, step 6, we do this by performing a multiply ERO. In this case, let's divide R2 by 10. Okay, so now we have leading one, but we still have a non-zero below this leading one, and that entry is 4. So, step 7, let's apply another ERO, R3 minus 4R2. Once we have successfully done that, step 8 is for us to look at the next column. Now, we also need to produce 1 as its leading entry. But what we have is negative 1 over 5. How can we do this? Let's multiply R3 with negative 5. Now, after doing all that, we finally arrive at this REF form, which we can use to solve for our x, y, and z values. So meaning, step 9, let's plug in z equals to negative 1 to the SLE. We get y equals to 0 and x equals to 2. So from here, we can see x, y, and z has unique solutions.
Welcome to our step-by-step guide on solving a system of linear equations using Gauss-Jordan elimination. Don't panic, we will make this super easy. First, we rewrite the system of linear equations into its augmented matrix form. Next, we use an elementary row operation or ERO to swap the second and first rows. This helps us organize the matrix for easier calculation. Now, let's produce 0 under the first leading one in the first column. We use EROs to eliminate the entries below. Note that we could use ERO to multiple rows at a single time as long as they are not dependent on each other. Since we have successfully produced 0 for the first column, we can now cover the first row and focus on the second row. To make solving easier, we need to produce a leading one in row 2 by applying another ERO. We multiply row 2 accordingly. Looking at the next column, we realize we still need to produce a 0 below the new leading one. Let's use another ERO to eliminate it. Moving on, we now need to focus on row 3. Let's produce a leading one there by dividing the entire row. By following the Gauss-Jordan elimination method, we continue clearing zeros for the remaining entries above and below our leading ones. Now, let's look back at the previous columns. We continue producing 0 for any remaining entries to fully simplify the matrix. And yes, now we are done. We can now easily solve for the variables. We find that x equal to 1, y equals to 2, and z equal to 3. Hence, the system has a unique solution.
Okay, for the next method which is inverse method. Okay, so let's recall about the theorem that we have learned in the lectures. Theorem 1.2. If A is an invertible matrix n by n, then for each n by 1 matrix B, the system of equations Ax equals to B has exactly one solution, namely x equals to A inverse B. Okay, next, let's do an example of question that use inverse method to solve the system of linear equation. So the equation is 3x plus 5y equals to -1, and the second equation is x minus 2y equals to 11. So the first thing first, we must write the SLE in form of Ax equals to B. So the matrix will become 3, 5, 1, -2. The second bracket is xy equals to, the third bracket is -1, 11. Next step, the second one is we need to find the inverse of the A matrix. So in order to find the inverse of A matrix, we must find the determinant first. So the formula of determinant is AD minus BC. So the A of the A matrix is 3 times by D, that is -2, minus 5 is B, and times by 1 of C. So the answer will get -11. The next thing is we must find the adjugate of A matrix, and it will become -2, -5, -1, 3. So the general formula of adjoint A is D, -B, -C, and A. So from A matrix, we must interchange the A and D position, while B and C we must put negative to the number. Lastly, we must inverse the matrix of A. So the formula is A inverse equals to 1 over determinant times the adjoint A. So 1 over determinant, we have find it, so 1 over -11 times with the adjoint A, that which is -2, -5, -1, and 3. The answer will get 2 over 11, 5 over 11, 1 over 11, and -3 over 11 for the inverse of A. The last step is we must multiply both sides of equation with the inverse of A. So the formula is A inverse A x equals to A inverse B. So we just substitute into the formula. A inverse is 2 over 11, 5 over 11, 1 over 11, and -3 over 11 times A matrix, that is 3, 5, 1, -2, and xy equals to the inverse of A, 2 over 11, 5 over 11, 1 over 11, and -3 over 11 times with B, that is -1, 11. So in the left hand side, the A inverse times with A will get identity, and xy will remain the same, equals to the right hand side, which is A inverse times B as in the general formula. So the answer will become 53 over 11 and -34 over 11. So the conclusion is x equals to 53 over 11 and y equals to -34 over 11.
The next method is the Cramer's rule method. The Cramer's rule method is if Ax equals B is an SLE with n equations and n variables such that the determinant of A is not equal to 0, then the SLE has a unique solution, and the solution is Xn is equal to the determinant of An over the determinant of A for all variables, where Aj is a matrix obtained by replacing the J column of A with B. One example is the following system of linear equations: 2x plus 3y equals to 8, 4x minus y equals to 2. The first step is to convert the SLE into the x equals b form, which is 2, 3, 4, -1 times x, y equals 8, 2. The next step is to find the determinant of A, which is AD minus BC, so 2 times -1 minus 3 times 4, which is -14. The next step is to replace the column of A to find the determinants of x and y. So for AX, we replace the first column with B. It becomes 8, 3 to -1. And the determinant is AD minus BC, which is 8 times -1 minus 3 times 2, which is -14. And for AY, we replace the second column with B. So it becomes 2, 8, 4, 2. And the determinant is 2 times 2 minus 8 times 4, which is equal to -28. The last step is to solve for x and y. X is equal to the determinant of AX over the determinant of A, which is equal to -14 over -14, which is 1. And y is equal to the determinant of AY over the determinant of A, which is equal to -28 over -14, which is 2. So x equals 1 and y equals to 2.